Okay, guys, let's get started. Um, as I announced on the Blackboard, so I believe some of you have registered for this course during the registration change period. So, and then, so test students, please read the syllabus on the Blackboard. So then, so so you need to know some rules for this course. Okay. Okay. So. Uh, okay, so in the previous class, we learned about the performance metric of computer systems. So actually, this is the main theme, the main topic of the first chapter of the discourse. So also, so you need to understand the main object of computer architecture research is to increase or improve the performance and reduce the cost. Okay, so it means you need to understand how to measure or how to compare performance of a computer system. Okay, so we learned that there are two the representative performance metrics for computer systems. The first one is response time, and then the second one, the throughput. So you need to also understand the meanings. The meanings of is two metrics. Okay. So we can call the response time is latency. Okay. So it's the code. So usually we use these two performance metrics, latency and throughput. Okay. Okay. So you need to understand the meaning of these two terms. And so, and then in the first chapter, we learned about the latency or response time, right? So it just compared the execution time of a task. Okay. So also, actually, you need to understand the definition. It's just the definition. So we can. So this is the uh, important thing. The performance is performance of a computer system is inversely proportional to the response time or latency. And we in order to measure the performance of a computer system, we compare. Okay, so we compare the performance of a computer system with another computer system or baseline computer system. Okay, so also I posted the first homework assignment, right? Okay, so and then if you simply read the instructions of this first homework assignment, so you can find the this sentence. So you are requested to compare. If you are requested to compare the performance, then you need to write a sentence like this: X is n times faster than Y, or X is n% improved by Y. Y. Now, compared to the system Y, X is improved by X%. Okay. N%, not n times. So you need to understand the percentage. Okay. So the clocking is also the basic knowledge on digital system. Okay. So I said that every digital system or every digital component uses clock signal. Okay. So, so in order to understand the performance, you need to also understand the clock signal of the system. Also, it means you need to also understand the clock signals on CPU or processor. So this is a very critical signal. Okay. So, so we can define a CPU time like this. The CPU's clock cycles. We can just count the clock cycles because the digital system, the working of the digital system is synchronized with the clock signals. So if we want to measure the CPU time, then we can just count the clock cycles. So 1,000 clock cycles or 100 clock cycles. Then multiplied by clock period. Okay, this is the CPU time. And then based on this equation, so we can make this equation. So this is a very important equation and measure the CPU time. So that CPU's execution time. It's so you can memorize like this. So P is the execution time. Instruction count, I see, multiplied by CPI, clock per instruction, and PC is a clock period. Okay, you can memorize this equation of this IC multiplied by CPI and multiplied by PC. Okay, so also I explained that if we just if we analyze the equation, then we can also figure out which factors influences the performance. Okay, so these are some factors like algorithm, programming language, compiler, instruction architecture, or microarchitecture, and hardware design, and semiconductor technology. So actually, all these factors influence the performance of a computer system. And we can focus on a certain factor for our study or research. Okay. So another performance metric is MIPS, is the number of instructions per second. But so in order to use MIPS as a performance metric, it means that we need to use the same ISAR or same compiler, which means that if the number of instruction or instruction count is the same, then we can use MIPS as a performance metric. Okay. So for example, if we just compare the two computer systems that use a different ISAR, such as x86 or ARM, then we cannot use MIPS, right? It is because the instruction count is different, right? So you need to remember. Okay, so that's what we learned in the previous class. And then, okay, so let's learn about another important factor in computer system. It's a power consumption. So I explained that as an engineer, so we want increase the performance and reduce the cost. The power consumption is the cost factor of a computer system, right? So computer system is an electric device, a kind of electric device. So which means in order to run a computer system, that we need to this computer system consumes electricity, right? Obviously, right? So, and then if we consume electricity, then we need to pay money. Okay, so this is the cost. Okay, so actually, another purpose of engineering is to reduce the cost. So, and then in a computer system, power consumption is the main cost of a system. Okay, so this is called the power wall. So it is because the development of a processor is is prevented by power consumption. It's the wall, so it's some hurdles, okay? So then the advances of the computer system is actually prevented by this power consumption factor. So let's see why. So this graph shows the power trend of a CPU. So as you can see, you can find the two y-axes here. So this axis represents the clock rate, the clock frequency. And then what is this? It's the power consumption. So you can find that this is the low scale and this is the linear scale. Okay. So in 1982, the clock frequency was 12 megahertz. It's very, very slow, right? Okay, so recently it's around the so for the desktop computer, it's around the 5 gigahertz. It's 5,000 megahertz, right? So compared to the current clock frequency, actually, so in the long time ago, the clock frequency of a CPU was very, very low. But you can also check the power consumption of this old generation CPU. It's around the 3.3 watts. Okay. It's just 3.3. It's similar to the mobile devices, right? It's very, very low. But we can observe that the clock frequency is has increased very dramatically. So it becomes the 66 and 200, and the Pentium 4, it's a 2,000 megahertz. It's 2 gigahertz, right? So this number is similar to the current number, right? So even though we are using the 5 gigahertz or something like that, but actually it's 3.3. Sorry. So this number, the 2 gigahertz clock frequency, is similar to the current number, current clock frequency of the modern CPU. Then how about the power? And the clock frequency has increased dramatically. The power consumption is also increased dramatically. So it reaches around the 100 watts. Okay. And then it is reduced. So why? Why in this period the clock frequency is increased? It's because we want to use good, better CPU. So it means that CPU can exhibit higher performance. And then actually, so we learned about this equation. So in this equation is the TC, right? It's the clock period. So in order to reduce the execution time, and then another approach is, so one of our approaches is to reduce the clock period. It means increase the clock rate or clock frequency, right? So in this period, we can increase the performance of a CPU by increasing clock frequency. And then also, it is based on the advances in semiconductor technology. So I also explained that if we use smaller transistors, and we can increase the clock frequency, because we can make faster devices, right? With smaller transistors. But also we can observe that the power is also increased, right? So it is because this is the power equation. The CMOS technology, the power equation is like this. Actually, this is proportional, okay? So not equal. So what's the power equation? Power equation is the capacitive load and then voltage square and clock frequency. So the capacitive load is actually proportional to the area of a chip. So you can find that you can think that this is proportional to the area of semiconductor chip. And then voltage is the supply voltage. Okay, just the supply voltage, and then frequency is the clock frequency. So actually, supply voltage is the square factor, but we can say that also if we use the same semiconductor technology, and then if we want to increase the frequency, then we need to increase the supply voltage. Okay, so it is frequently said that usually the power is proportional to the device. Power the power is proportional to the cube of clock frequency. If we use the same semiconductor technology, because actually the voltage, supply voltage is proportional to the frequency. Okay. So if we are interested in desktop computer, and then actually we can increase the performance of the desktop CPU by overclocking. So what is the overclocking? So actually, let us assume that the 3 GHz is the recommended clock frequency, but actually we can increase the clock frequency of a CPU, but in order to increase the clock frequency of the CPU, then we need to supply higher voltage. So this is the basic approach of overclocking. So the benefit of overclocking is that we can increase the performance of the CPU without purchasing a new CPU, right? But that's the problem. Power is increased. Okay, so you can understand like this: the voltage is proportional. So frequency is proportional to the supply voltage, and then based on this power equation, actually the power is proportional to the cube of frequency, the clock frequency. So what's the matter? So we want to increase the performance, right? And then actually the easiest way, the direct way to increase the performance is to increase the clock frequency, right? But what's the matter? Power. So this is the example. Also based on this equation, then we can also compare the power consumption. Okay, so you can just use some information like the 85% of capacitive load or some supply voltage or frequency. Then we can calculate the power consumption like this. Okay. So and then based on this equation, then we can also figure out how to reduce the power consumption. How? So if we reduce the voltage, then we can reduce the power consumption. Also, if we can reduce the capacitive load, then we can reduce the power consumption. But this is proportional to the area of chip. So actually we cannot, after the chip is manufactured, so we cannot change the chip area. So we can just adjust the voltage and frequency, right? But problem is that, so actually in order to, so I explained that in order to increase the performance of a transistor, then we need to use the smaller transistor, right? So it is a, so we can, so smaller transistor is usually faster. So which means that usually 3 nanometer transistor is a technology node is faster than 10 nanometer technology, which is just usually, okay, not always, it's usually. But problem is that supply voltage. So actually, I will not explain about the some mechanism of the transistor. It's out of the scope, but actually, even though we reduce the size of transistor, then we cannot reduce the supply voltage further. So actually, when the size of transistor is changed like the micrometer scale, so actually, and then basically, when we reduce the size of the transistor, then we can also reduce the supply voltage. Okay, this is the some main basic property of the transistor. But now the transistor size is the nanometer scale. So it's a very small. And then for the very small transistor, it is very difficult to reduce the supply voltage. Okay, so that's the problem. Also, the transistor now dissipate the more heat. It's also very critical. So usually the heat, we can say that the heat is proportional to the power consumption. So we can find that the modern CPUs or modern GPUs includes the very heavy fans, right? Why? Because we need to reduce the temperature of the CPU or GPU. So why? Because CPUs or GPUs work properly in the range of a certain temperature range, right? So if the temperature is very high, then the chip is broken, just broken. Okay, so that's why we require. So in the computer system, we require the cooling system, right? Like a very large electric fan. So, but it's very hard. It's very hard to remove the heat. So nowadays we can use the water cooling system, right? So it is because the cooling is very hard recently. Okay? So this is the power wall. Okay, because of the high power consumption of a processor, then we can. It's not easy. It's not easy to make better computer system, but it's not easy to make better CPU or GPU, okay? Because of power, okay? Then how can we improve the performance? So it's not easy to increase the clock frequency because of power consumption, okay? Then how can we improve the performance? Okay? Multi-processor, the multi-core architecture. Okay. So actually this slide explains about the Dennard scaling. So it's a scaling of dynamic power. Okay. So Dennard scaling is that the power density is constant. Okay. When transistor scales down. Okay. So sorry, my writing is not good. But you know, that is very bad. So So this is the Dennard scaling, the power density. Power density is the power consumption, per area. Okay, so this is the power density. So Dennard scaling is the power density is constant when transistor size is reduced. Okay. So because of this factor, so this is the dynamic power equation. So it's the same to the equation we learned. Is the C is the capacitive load, and then VDD is the supply voltage, and then F is the frequency. Fine, it's the same. And then alpha is the activity factor. Okay. So I said that the P is proportional to the C, VDD, here and F, right? The same equation. And then when we reduce the size of the transistor by S, then C and VDD also reduced like this. So I mentioned that traditionally, and then the old generation, when we reduce the size of the transistor, then we can reduce the supply voltage level. Okay, so we can reduce this one, and then but the frequency, we can also increase the frequency. So in order to increase the performance, we can increase the frequency. So P dynamic becomes the 1 over S square, but because the size of a transistor is reduced by S, then in the same area, we have S square transistors. So if we just multiply 1 over S square, multiply S square, then it's 1. Okay. So Dennard scaling. So Dennard scaling explained that. So if we can reduce the size of transistor by S, but the power density is the same. Power density is constant, but we can increase the performance because we can increase the clock frequency by S. So it's very good news, right? Why? We can increase the clock frequency performance of the CPU without sacrificing any power consumption. Okay. So this is the Dennard scaling. And then this is the benefit of the semiconductor scaling. But this is the real trend. So you can find the two y-axes, like the technology node and then power density. So you can find the power per square nanometer. So this is the technology node, the size of the transistor, actually the width of the transistor channel. So it is reduced like this. So based on the Dennard scaling, first, this is the power density. So power density should be constant, but actually it is increased, right? So Dennard scaling is the kind of old trend. Okay? It does not work recently. It does not work. It worked in the previous time, the previous generation, but now it does not work. So it is called the end of Dennard scaling. Okay, so nowadays the power density is not constant. So that's the problem. Even though we can reduce the size of transistor, but the CPU or GPU consume more power. Okay, and then I mentioned that the power is the kind of war. So actually the power is also very critical cost factor, or is also constrained from manufacturing process. So it means if the power consumption is very high, it's also difficult to make a chip. In order to make a chip that consumes much power, then we need to the manufacturing cost is also increased rapidly. Okay, so that's why if a chip consume much power, the chip price is also very high. Okay, like GPU. So GPU has another reason, such as the supply reason. But anyway, the GPU consumes much power, so the manufacturing cost is also high. Okay, so this is the power wall. The power is increased, so and then it's not easy to increase the clock frequency. So then how can we increase the performance? So I said that there are two representative performance metrics. Okay, the first one, latency, is a response time, and second, throughput. So actually, not to increase the latency, it's actually the execution time is the instruction count, CPI, and TC. Actually, the hardware cannot reduce the instruction count. It's the software part, like the instructions and architecture, compiler, or algorithm. So hardware can improve the CPI. So by improving the microarchitecture or TC. And then TC is actually we can improve, so we can reduce the clock period with the better semiconductor technology. But I explained that nowadays this is very, very hard, okay, because of power consumption. And then this part is the software part. So it's not easy. It's not easy to reduce the latency of a task. But we can increase the throughput using multiprocessors. How? So think like this. So there is one worker, okay? And then this is task. So workload, the task that needs to be done by this worker. Then we want to increase the performance. Okay, so one of the way to increase the performance of this worker is to increase the performance of a single worker, right? But in order to reduce in order to process the same task in a shorter time, another way is to increase the number of workers, right? Right? So we can increase the throughput. So throughput is the amount of work or task done for our unit time. Okay. So now to increase the throughput, then we can increase the number of workers in our real life, right? It's the same. So we cannot improve the latency of a single task, a single thread. But we can increase the throughput by increasing the number of processors, the number of cores. Okay? So this is called the multiprocessors or multi-core architecture. Okay. So nowadays, the mobile processors also employ multi-core architecture, right? So you know the Samsung Exynos so includes 8 cores. Like I don't know the exact number of cores, but usually 4 big cores or 4 smaller cores, right? No, little cores. Right? Also, Intel desktop CPU or laptop CPUs also. i7 or i5 includes multiple cores, right? So recently the Intel changes the brand name of the cores. So anyway, so actually every CPU is a multi-core CPU essentially, right? Why? It's not easy to increase the length frequency, right? So which means that it's not easy to reduce the latency of a single task. But recently, a computer system execute many tasks concurrently, right? So we can improve the performance, throughput. We can improve the throughput by increasing number of cores. This is the switch to multiprocessor. Okay. So, so this graph shows the performance change of uniprocessor. It's a single processor by year. And then also you can find the y-axis is here. And then you can find the cursors, BAX. So it's just the relative performance, right? Right? So this is the baseline. We just compare the performance of a processor with the BAX. So we can find that during this period, the performance is increased by 52% per year. And then this is the low scale, and then it's a linear. It doesn't mean it means performance is increased exponentially. It's a dramatic increase. It's a dramatic improvement, right? So actually, in this period, the performance of CPU is increased because of advances in semiconductor technology. Okay. And then also during this period, the slope is reduced. But anyway, it's increased. But we can observe that recently the performance of a single processor, a unit processor is saturated. Okay, so it means for a single task, it's not easy to reduce the latency. Okay, so the performance is saturated, but we want build and we want to use narrow computer systems, okay, higher performance computer systems. So we can use the multi-core architecture. So it's an easy way. Oh, we want to increase the performance and we want to increase the throughput. Then we can just increase the number of workers. So we can increase the cores. So very easy, right? But what's the problem? What's the problem of multiple workers in real world? So, for example, so you are doing a project, it's a Tom project, then you can build a team. Okay, so you can build a 2 people per team. So you can build a 4 people per team. And how about the performance? The team A and team B. So if we just compare the performance, then performance of team B is the 2 times of performance team A. in real life? Yes or no? So, right, so this is your top project, you are building a team, so you can, you can get also more students, so like four people per team, then performance is higher. So it's a 2 times of this team, 2 people per team. Actually, not, right? It's true, right? In real life, right? Even though the more people, like n people is participating in a certain team, but the performance cannot be n times, right? There are many factors. So like so actually enough to increase the performance, then we need to we need to split the task to the 4 parts, like n parts. But actually, all tasks cannot be split, cannot be divided. That's the one problem. So actually, it depends on the property of the task. And then another problem is overhead, like the communication overhead, or some scheduling overhead. Right. So communication overhead is that. So even though the tasks can be split to the end part, but actually we need to communicate each other to complete the whole task. Actually, it's not easy, right? So it's the same. It's the same for the multi-core architecture. Actually, so because of this part, the programming for performance. So parallel programming is usually more difficult. So we are familiar with the single-threaded code. So which means we can just write the code, but we assume that this code is executed from top to bottom sequentially, right? But we already know that in the single-threaded performance, the performance is just saturated. It's not easy to increase the performance of a single-threaded application. So, which means we need to write parallel programming code. Okay, so which means that the tasks need to be divided into n parts. And then these parts, the parallelized parts, need to be executed concurrently, simultaneous, right? So, but it's not easy. Parallel algorithm, oh, it's not easy. The parallel algorithm is much more difficult than serial algorithm. Also, programming is not easy. This is the one hurdle of the multiple architecture, and then the load balancing. So as tasks need to be split fairly, but it's not also easy. Okay. Also, communication and synchronization. So I also mentioned that there is a communication overhead for the real world. It's the same for the computer system. Actually, the input and output and some parameters need to be communicated with the separated task. But you can also observe communication overhead in the computer system. So synchronization issue. Okay? So it's not easy, but actually, so the computer system is changing to the multi-core systems. So actually, so we need to exploit this multi-core architecture. So because of this power consumption factor, we need to use the multi-core architecture. It changes to the multi-core architecture. So it's a trend. So now every computer system includes the multi-core CPU. Okay, this is the change of the computer processor architecture. Okay. And I will briefly explain about the benchmark. So we want to compare the performance of a computer system and how. So in the previous class, we learned, you can measure the CPU time, the response time, like the and then CPU time is the instruction count and CPI and TC. But the CPU can actually run any applications, right? Then which applications need to be used for measuring the performance of a CPU? So we need to decide. So we can use benchmark. So actually, there are a bunch of applications, right? But we cannot use these all applications for measuring the performance of our system, right? So then we need to select the representative applications for measuring the performance of a CPU. And then these applications are called benchmarks, okay? So benchmarks, and then a set of these benchmarks is called a benchmark suite. Okay, so there are many benchmark suites. Then actually, for the CPU benchmarks, we frequently use spec benchmark. Okay, so spec means the standard performance evaluation operation. Okay, it's a spec. Okay, actually, some manufacturers, such as the computer manufacturers and CPU vendors, just make this group, a spec group, and then they select some applications, and then these applications are commonly used for measuring the performance of a system. So you can Google spec benchmark, then you can find some more recent spec benchmark, and then also you can find some descriptions about the spec benchmarks. So actually, the spec benchmark has many different applications, like the C into 2006 or CFP 2006. So C means the CPU. So this is a CPU, and int is the integer. And then also CFP is a C is a CPU, and then FP is the floating point. Okay? So these benchmarks are used for measuring the performance. But as I mentioned, the benchmarks, the applications includes the different proportions of instructions, right? So sometimes we can use some applications include more integer instructions, or some applications include more floating point instructions. So we can use these benchmarks for the different purpose. So in order to measure the performance of floating point arithmetic, then we can use the CFP. Okay? And recently, the most recent version of spec benchmark is the 2017. Okay? This is 2006. So this is the list of example of spec benchmarks. Okay? You can find some different applications like the GCC, PowerBench, or X264. Okay? And then you can also find the description here. Okay? So CPI is here. You can find the instruction count. Okay? The CPI. and clock cycle time is what is this? It's TC. Okay, so actually in this table you can find the information for measuring the CPU time, CPU execution time. So you can calculate the execution time here, and in order to measure, so actually I explained that in order to measure the performance, actually we need to compare the performance with the baseline machine. So you can find the reference time. So reference time is the execution time by baseline machine, the reference machine. Okay, and we can compare the execution time, then we can get the performance of this target machine. So this is the spec ratio. So actual spec ratio is the, you can find that spec ratio is the reference time divided by execution time. It's the same. It's the same the performance comparison. Okay, I explained that performance of system X is n times faster than performance of higher than performance system B. So like the, you can just compare the execution time. It's the same. Spec ratio, it's just the execution time of a target machine. The reference time is divided by the execution time of a target machine. Then we can get the spec ratio. And then by applying geometric mean, then we can get the spec score. So the spec score is the 2.36. So it means this target machine, this is target machine is that how many times? 2.36 times faster than reference machine. Okay, this is the meaning of spec score. Okay. So also another spec benchmark is the spec power benchmark. So the spec benchmark is to measure the performance, the performance of a CPU, but we can also measure the power consumption of a CPU. So this is some equation of the spec power benchmark. We can find the somewhat it's not easy to analyze, but we can just understand that the spec power benchmark just measure the performance per power consumption. Okay, so this is also very important metric, the performance per power consumption. So if you just Google just compare some processors, so you can also find this metric, the performance per power. Okay. So, but when you apply the spec power benchmark, we can observe some interesting aspects. So this is the target load, and then this is the performance, and then this is the average power. So actually the spec power benchmark is used for measuring the power consumption of server computer systems. Okay, and then the server is the very high performance computer system, and then server is designed for running many tasks, many concurrent tasks, right? So the target load is the the percentage of load to the server. 100% means that actually the task occupies the 100% of its server resources, right? So we can find that there is 100%, and then the average power is the 347, and then the 10% average power is 115. So it's a 10 times. Workload is 10 times. So which means that the performance is the 10 times compared to 10% to the 100%. So how about the power? Power is around the 3 times. So what does that mean? Actually, this situation, if we just compare the power, no, performance per hour, this situation is bad. Okay, so performance is around the 10% of the maximum performance, but this system consumes around the 1/3 of power, the maximum power. Okay, so power is wasted. So actually, we can observe this property to the server. So actually, in order to actually for the server system, 100% load is the most power efficient actually. So this is another some research topic. So the power is not proportional to the target load, the load of the server system. Okay. Okay, so I briefly introduced about some benchmarks, like the spec benchmark and the spec power. Okay. Okay, then. So let's learn about the Moore's law. So if you are interested in CPU, then I believe you can you have heard about the Moore's law. So what is this law? Actually, this is very popular law in semiconductor industry. Okay? The Moore's law, the performance or number of transistors. The Moore's law says the number of transistors. So you need to understand that. So number of transistors, not performance, will double every 2 years. So this is the Moore's law. So Moore's law represents that the number of transistors. The number of transistors will increase, but it's double every 2 years. So what does that mean? In the same area, in the same chip area, we can include more transistors, okay? More transistors, but this transistor density is increased exponentially. It's a double by time. So it means it increases exponentially, not linearly. So linear is it's a different. So linear is just linearly increased, but this Moore's law says that the density, the number of transistors per unit area, is increased exponentially. Right. So it means also we can reduce the size of a transistor. Okay. So this is the Moore's law. So why Moore's law is important? So actually the Moore's law is It's not a theoretical law, it's the empirical, it's based on the some empirical data. Okay? So who is actually Moore? So the Moore's law is was represented by Gordon Moore. So Gordon Moore is the actually co-founder of Intel. Okay? And he recently died in 2023. So he's a co-founder of Intel, and then he just observed the trend of the CPU development. The number of transistors in a single CPU, right? And then he found that just a trend. Okay, so he found that the number of transistors per unit area increases exponentially. Okay? So this is the Moore's law, and then actually, so this is not a theoretical law. It's just an empirical observation. It's just an observation actually. Then why? Why Moore's law is very popular in the semiconductor industry? So it is because the semiconductor industry just set a goal, a technology goal based on the Moore's law. Okay? That's why Moore's law is very popular. And then, so until recently, the Moore's law is just worked. Okay? So it means, so recently, the semiconductor technology is very critical, very critical for the industry of a nation. So you can find that TSMC is using a 3 nanometer, well, Samsung is developing 2 nanometer technology. So it means that they are reducing the size of transistor, and that's based on Moore's law. They try to reduce the size of transistor based on Moore's law. So it is just observation and it is just a trend. Okay? So it means if the Moore's law continues, then it means we can use smaller transistors, or we can use better transistors. Then we can easily increase the performance of a computer system. That's Moore's law says. Based on the semiconductor technology, we can reduce the transistors. We can reduce the transistor size, and we can increase the number of transistors per unit per area. Then we can increase the performance. It's Moore's law. So this is a real trend. So this is the y-axis is the year, the time. And this is the number of transistor count. So this is the log scale. You can find that the number of transistors per chip or per processor increases linearly in this graph, but it means exponentially. Okay? Increases exponentially by Moore's law. So this is the target. This is the goal of the CPU vendors. So we can make the CPU, but based on the Moore's law, so they have developed their CPU. Okay? So transistor count increases exponentially. Okay? So this trend shows the microprocessor trend for 40 years. So this is a transistor count. So this graph shows the Moore's law. Oops. This graph shows the Moore's law. So it continues until 2020. Then, but we can find that the single thread performance is saturating. Then frequency is also saturating. And then also typical power is saturating. but number of cores is increasing. Okay, so this is the trend. So even though the Moore's law continues, we cannot increase the frequency. We cannot increase the performance of single-threaded application. But we are living in the multi-core era. Okay, so this, we can use the multi-core CPU. So number of cores is increasing. Okay, so actually the Moore's law continues. But recently, so this trend is changing. So someone say that the Moore's law is ending. Then also Gordon Moore actually said that the Moore's law will end shortly. So it means we cannot use error transistors. Okay? Gordon Moore also said that Moore's law will end shortly. So, but based on the Moore's law, so we have developed a CPU. Okay, and then we can make the better CPU. So this is the 8 great ideas in computer architecture. Okay, so you can find the design for Moore's law. So it's not just a trend, but based on this trend, we just set a goal of the CPU development. Then we design the CPU based on the Moore's law. Okay. So this is because the CPU is based on the semiconductor technology. So we just predict this semiconductor technology, and then based on the predicted technology, then we have developed the CPU. Okay, and then I also explained about the abstraction. So we can use the abstraction manner for understanding a certain layer of a computer system, and we can simplify design. Okay, and then this is some ideas. So make the common case fast, and then parallelism, pipelining. So we learn about the pipelining in this course. So I think that this is the very important thing we need to learn in this course, the pipelining. And then performance is improved by prediction, and then hierarchy. So this is another theme we need to learn in this course, the memory hierarchy. And then dependability via redundancy. This is for reliability. So actually, the computer architects have developed the better CPU based on these approaches. Okay, so 8 is called the 8 great ideas. So in the textbook, actually, the Hennessy and Harrison mentioned these 8 great ideas. Okay, so this is the end of chapter 1. So we learned. So this chapter 1 is just an introduction to the computer system or computer architecture, and then so we learned that a computer system is composed of many layers, and then in order to understand the computer system, then we can use some abstraction manner. Okay. So it's frequently used in our real life. Also, so in the computer system, we frequently use abstraction. Okay, and then so we learn how the programs are compiled, and then instructions are generated, and then instructions are executed. Okay, and then we will learn about some detailed instructions in chapter 2. Instruction set architecture, and then execution time. So in order to measure the performance, we can measure the execution time. And we also learned how to measure the execution time. Okay, so as I mentioned, the IC instruction count multiplied by CPI and TC is a very important equation in this course. Okay. Then power is a limiting factor. Okay. So because of power consumption, we can, it's not easy to build a better CPU. Okay. So the computer, the CPU is trend is changing. Okay. The trend of CPU is changing because of power. Okay. Okay, this is the end of chapter 1. And then, okay, so I'll stop here. Any questions? Okay, thank you for attention. We'll see you in the next class. And have a good Chuseok. 감사합니다.